So those announcements will be coming down soon. I'll post those on A2L. That way everybody has them. I got feedback last year that it was a bit weird having like the teams and A2L as sources of information. So I'll try and keep everything onto A2L. Is that better? Okay. Can do. Okay. Iterative methods. Gaussian elimination, LU decomposition, all those are direct solvers. And what that means is that they will find the solution in a set number of steps, right? So when we were doing the Gaussian elimination, you take your pivot row, you subtract by the next one, you eliminate that. You take that one, you subtract by the next one, you eliminate that. We talked about it, and for dense matrices, that scales terribly, right? It scales order n cubed. For sparse matrices, especially like banded and things like that, and like structured sparse matrices, it becomes faster and significantly faster. And on the assignment, you have that. You can see like that working. But generally speaking, for large enough systems, it gets to be a bit problematic. They are, however, the most robust, right? So again, with COMSOL, your direct solvers and the modern direct solvers are kind of like your go-to. I would say safely until you're at the point where you've nailed down the physics and the equations and you're like fine-tuning stuff. So again, in COMSOL, almost all the time are the solvers that we use were the direct solvers. In few exceptions on your reports, maybe you had like multiphysics and then you had like Navier-Stokes along with heat transport and this and this and this. COMSOL underneath the hood was doing something called a segregated solve, which is the I think we'll probably come to with preconditioners. So on Friday, we'll come to that one. But the idea is that you solve this, and then you solve this, and then you solve this, and this, and this, and this, and this. And then you bring the solution, and hopefully it converges. Yeah. We're now going to shift over to something called iterative methods or indirect solvers. What they do is they take an initial guess, and they try and improve it and improve it and improve it and improve it. Hopefully, you will get to a solution. There is no guarantee. If your matrix is not well conditioned, right? And remember, it's kind of this idea of like the separability of those equations. Parallel equations don't have a solution. Don't expect your indirect solver to find one or your direct solver to find one, right? You're only going to get that one with the pseudo inverse, and we'll get to that one soon enough. If it solves, then it can be much more memory efficient, and it can be much faster. However, sometimes even just the act of looking for that solution and iterating on and on and on can take so much time that you may as well have just done a direct solve in the first place. Guess what the rule of thumb is? Anybody want to take a guess what the rule of thumb is? That's a very good one. Yeah. Anybody else? Okay. Anybody else? Honestly, I would probably do that, to be honest. The iterative solvers are great when they do work, but sometimes there is no rhyme or reason to them. If you have like a code that's kind of mature, like the SCO neutronics code, what Paul is going to be talking about at 10 o'clock, and you're just doing the same physics over and over and over again, maybe you've got an iterative solver that maybe is demonstrated, maybe for that particular type of physics, maybe with those parameter regions, maybe it's going to converge well, right? There is no good rule of thumb. Direct solvers are kind of the most robust. So with the COMSOL course, like, I shouldn't call it that. With the computational multiphysics, what I advised was, like start up the direct solve, have your memory performance monitor watching, right? And if the memory like crosses that 90-95% threshold, emergency kill. And then you go for the iterative solvers. Honestly, like practically, it's sometimes just cheaper for the company to just buy you a bigger computer. Right? Because like the amount of time it takes for you to get an iterative solve working versus getting a bigger machine. At CNL, we had this problem. We said, hey, manager, I want to buy this new computer. It's $10,000, right? They said, sure. Because honestly, our billable rate when you're working there is $250 an hour, right? So whatever 100,000 or 10,000 divided by 250. Somebody good at math around here, numerical methods. Is it 40? Is it 40? I think that sounds about right. Right number of magnitude, right? Even at like a week of effort, it's going to take you more than a week to get an iterative solver robustly working. A new computer will solve that problem for all the problems. So anyway, that being said, iterative solvers. Okay, iterative solvers. I should amend this. Useful iterative techniques require certain properties. First of all, they have to be self-correcting. If you get into a situation where a little error caused by everybody's favorite round-off error, right, propagates and get worse and worse and worse, are you going to ever get to a good solution? Obviously not, right? You're going to fall off the mountain. The good ones have to be self-correcting. That's actually one of the principles that we're going to be hearing a lot about. Generally, they're more conducive to sparse matrices than the direct solvers are. The direct solvers, and there is the SPSLU solve that I think probably half of you guys saw in the assignment yesterday. You must have found it in the notes. Did you guys find it in the notes? Okay. If you didn't find it in the notes, it's in the direct solver right at the last one. You go all the way down to the bottom and it gives you the SPS, or you just Google it on Numpy or something. They are specifically designed for the sparse systems, but the iterative ones, because you can target individual elements, I'll show you what that actually means. They're generally a bit more, they have a little bit of an edge on the direct solvers. You had a question? No, just no, okay. Okay. You guys haven't done Newton's method yet, have you? You have done? Okay. So we're going to come around to Newton's method in a minute. If you haven't done in a minute, in group finding, in 2 weeks, we're going to come to Newton's method, right? If you haven't done Newton's method, no worries. Newton's method, you solve for the slope at every point, and then you do that linear extrapolation. Guess what? That linear extrapolation is a linear solve, right? Every time step, you have to recalculate that slope, right? Because you start off with 1, you calculate the slope, you solve. Now you have a new slope, you solve. Now you have a new one, you solve. That's not how linear iterative solvers work. In linear iterative solvers, all you're adjusting is your solution vector, not the matrix. Very big difference. Yeah? Okay. There is a class of solvers called matrix-free methods where you don't even need to have the matrix A at all. What you need is the matrix vector product, A of X, instead of A, which you then multiply by X. We're not going to go into matrix-free methods. It's a bit more advanced. But if you get into like if this becomes a research project on into the future, that's actually, I would say, probably one of the best modern approaches to this sort of thing. I think COMSOL does do it in certain situations. Unfortunately, that actually requires a lot of preconditioning, which again we'll get to. Okay. Each iteration will hopefully converge towards a solution asymptotically. You will never get the right solution. You will only ever be last and one. Good enough. Right? Again, we're coming down to the idea of tolerance, saying that either, right? Well, we'll talk about it in a second, actually. I won't spoil that one. Okay. How do we quantify convergence? How do we know when we're good enough? What is the ideal? So, if we know what A is, we have a guess for X, and we know what B is, right? We know that. We know that. How would you know if you've got the right X?
Solve A times X, and let's see if you get B.
Exactly, right? Super easy. All you can do is, yeah, so it's that, move B over to the other side, minus B is equal to R. R is called the residual, okay? And when R is approximately 0, you have solved your problem. So a lot of solvers, when they're talking about this tolerance, remember they're not interested in, so R is a vector, to be clear. Right? Here's where tolerance gets a little bit funny. People will define good enough as being the norm of R being less than the tolerance. Which tolerance? We've got two tolerances. We spoke about two. We talked about absolute and relative tolerance. Who has a guess which one is appropriate? You've answered a bunch. Somebody who hasn't answered. I'm going to start calling on people. Yeah. Okay. Anybody who agrees with absolute tolerance, raise your hand. Okay. Anybody who agrees with relative tolerance? See a lot of people who haven't even raised their hands. Everybody is wrong. The actual answer is both. The absolute, it's makes a lot of sense, and it's very tempting to go with the absolute tolerance because 0 is an absolute number, right? You can tell when you're getting to 0. The funny business is that in a lot of situations, the total magnitude of x doesn't actually matter, right? Because one of these other things is scaled, maybe the solution is scaled. If this gets scaled by a, you can multiply a by x minus ab, right? And then that a becomes part of your absolute tolerance. Does that make sense? Should I write that down? Okay, you've got this equation. We're going to multiply through by just the regular old constant a, right? That's distributive. This becomes ax, ab, because you've got some scalar multiple of your solution there, b, or your left-hand side, right? So now your r actually becomes ar, right? And therefore ar being 0, the absolute value of that, maybe it's useful, maybe it's not. Relative tolerance. I saw a lot of people saying relative tolerance at the back. Somebody want to tell me why relative tolerance would be good? Anybody? Yeah. Right? You could just cancel that out, and you could say that your delta R, because it's a constant, canceled out, and any scale that goes like that also goes away. The problem with the relative tolerance is if you have slow convergence, if you're getting there, but you're getting there really slowly, then does that make sense, right? Because you're iterating on x. If you're not taking large enough steps, then that can go really slow, and then your relative tolerance flips, right? And you exit, even though this is actually kind of far. So, for example, you could do say your first residual was 1, right? Your next one is 0.9. Your next one is 0.85, 0.84. 0.839, right? Has this converged? Maybe not. Maybe the answer is 3. And eventually you'll get there, but you're getting there super slow. Right? There are other ways to characterize that, and spoiler alert, that comes down to diagonal dominance. Yeah. Yes. Don't. Is the answer. Have both. Yeah. So generally, the best mode of practice is to just have both, right? You calculate your residual, you calculate the absolute tolerance, you calculate the relative tolerance, and you see which one works, and then you take a look at your solution. If it's reasonable, you're good. If not, then you have to go back and tighten things up. So the problem with the absolute, just to review, if you have ax is equal to b, or ax minus b is equal to 0, or r, right? And r being 0, right? If you have a scalar here and that multiplies through, then the magnitude of x doesn't really matter. It's not actually meaningful because you can always multiply through by a constant, right? In which case your absolute tolerance isn't really your best guess, isn't really your best measure of having got the right answerness, right? Similarly, if you are converging, but it's taking a long time, So if this eventually did go, right, you got 1.9, 0.85, 0.84, 0.839. The actual answer is 0.3. You're very, very far. And the absolute tolerance would probably say, not even close, right? But your relative tolerance is going to say, well, I'm slowing down, so I must be kind of close to the solution.
Yeah,
Yeah,
like,
please.
just like have constant time steps and jump around like the ideal convergence point.
Ooh, predictor corrector methods.
Oh.
That is an approach. We're going to be talking about that one with, I want to say, time stepping. That's a good approach for time stepping. The problem with this one is frenetic behavior, right? Which is a fancy way of saying that some systems behave terribly with that. We're going to see actually Thursday, we're going to see situations where I don't want to spoil anything, but you can kind of imagine this as the surface of a valley. And sometimes valleys will have like a very shallow slope in one direction, very sharp walls on the side. And if you're on one of the sides and you take a little step, you've jumped over into the nether instead of staying like kind of in the valley. So, okay, there is one more tolerance that we did not talk about. Anybody take a stab? Otherwise, I'm going to go into the back corner because you guys are quiet today. Anybody else have any ideas? It is the third missing tolerance. You guys want to take a stab? Person beside Mateo, like desperately trying not to be called on. Yeah. I'll give you a hint. What are we actually trying to find? This is what we're actually trying to find. So why aren't we checking a tolerance on this guy? Could we check a tolerance on this guy? Obviously, the answer is yes. Prof says, could you do anything? Obviously, the answer is yes. So a lot of linear packages, COMSOL including, but also PETSI, which is the a big one out of Argonne. I forget what it's called. Portable Extensible Library of something. They also define your solution tolerance. And the idea there is that, yes, the residual might be approaching convergence. Yes, it might be like not changing anymore, but you could also look at the solution itself. If the solution here, this is the R value, right? We could also say, is X decreasing and has it stopped improving? Has it stopped changing? Right? Which is a perfectly legit thing to ask. Technically, X not changing anymore means that your solver has stalled. It doesn't mean that you found the solution. Same way as this means that you've stalled, right? You've slowed down too much. You haven't found the solution, you're just slowing down too much. Different things to raise the two guys. One more wrench. What does this symbol mean? Right? Not quite. Norm, right. What does norm mean? Yeah, but it is a vector, right? How do you calculate the norm? Yes, there you go. So the vanilla way to do it is Pythagoras, right? In which case this norm, because R is a vector, the norm of that vector is the magnitude of that vector. Make sense? Okay. Or the other one that I pointed out, I think it was last week, was the L infinite norm. So the magnitude, the Euclidean Frobenius norm is the L2 norm. What it means is that you take all of your elements in your vector, you square them, sum them, take the square root, right? It's, yeah. Okay, that's Pythagoras. The L infinity norm is mathematically all the elements raised to the power of infinity added, and then you take the infinite root. What that actually means, because that's gobbledygook, right? What that actually means is that you take the maximum value. And that also kind of makes sense. Because if every element of here has, like, every element is kind of its own measurement, and you want your solution to have found where none of those elements are still changing. if you have 3 elements in X, 3, 1, 2, and your next guess is 2, 1, 2. The L2 norm, the Euclidean Pythagorean norm, between those two is kind of small. But one of these elements is still dramatically changing. And that's what your L infinite norm is going to pick up on. This is particularly problematic with multiphysics. COMSOL handles this. I think 1 or 2 of you guys, I took you aside and showed you the variable scaling. I don't know, did I talk to anybody about variable scaling in the room? Might have been some people with when we were trying to get their solvers to work. That's what we're actually doing here. We're trying to increase the sensitivity to some of those elements. Yeah? Any questions before we go on to how on earth we actually... No. Any questions before how we go to we don't do it? Okay, one more. Yeah. That's correct. Right? So the idea is that you are close to the solution plus noise. Noise will shift your direction, but as long as you're close enough, you're within round off. So you're never going to get to the solution because of your round off error anyway. So all you can say is you're close enough, but you don't really care about how far you are from that point. Exactly. Yeah. All right. Stationary methods. These are the fundamentals. Nobody does it this way. But pedagogically, it's important that we talk about it. All right. One class of iterative solvers repeatedly applies the exact same operation to the vector over and over and over and over and over again. What happens is that we pull that matrix apart. I'm going to show you how that happens. We don't decompose it. This isn't LU decomposition, despite the fact that we're about to describe L and U. This is not LU decomposition. This is literally ripping that matrix apart exactly as it is. And what you do is you manipulate that to form an update equation. This is in contrast to the methods we're going to talk about on Thursday, which are called Krylov subspace methods. That's actually the modern approach. But these are pedagogically important. Okay. What does it mean for a value of X? I'm going to ask this rhetorically because I want to make up the time. What does it mean for X to actually solve this equation? Right? What it means is that all of the individual elements of X are consistent with each other. This one, there is only one solution. First of all, linear system, well-defined, well-conditioned, there is exactly one. And that one implies that whatever this element is, it's consistent with these other 2 elements. So could we take this matrix and assume that these 2 guys are consistent, are correct? And what would this element have to be in order to match up with these 2? Right? So the idea with this is that we're going to start with a guess, right? And we're going to state for every step, we're going to identify a single element in the solution vector and update it. We're going to make it consistent with the other ones. And we do that around and around and around and around and around. We go down all the lists. We start at the top and we go down again. We keep going until we aren't changing anymore. Or we've satisfied any of our tolerances or all of our tolerances. Okay. Jacobi iteration scheme. What we do is we start off with AX is equal to B. We write it down in component notation. It gets a little bit messy. As I've said, like these guys are kind of like their historical ones. Successive over relaxation is actually something you'll probably run across if you do continue in this, but it's going to be a subcomponent of something bigger. Okay, so learn this one conceptually. Don't worry about the details with the notation. The idea, what you're doing with this one, is that you're going to extract your ith row, right? So this is an iterative thing. You're going to loop through all your rows. You're going to take one, and you're going to solve for the diagonal term, right? So you're going to extract that guy. You're going to shift everything else over here, and you end up with this update equation. So you want this particular element. You extract that from this solution, and you solve. What would this have to be, assuming that these guys are correct? You can write that as a matrix form by just pulling apart this matrix into UDL. This is not decomposition. I tried to come up with a different cis symbol instead of U and L. Don't be confused. Not. I couldn't come up with a better variable. I thought lowercase, but then all the uppercases are matrices. So we're not going to talk about this again. So just go with this one. Okay, suspension of disbelief. Okay, what you're going to do is you're just going to rip this thing apart. I don't know why there's a 0 here. It shouldn't be a 0 there, right? You've got your lower, you've got your diagonal, you've got your upper, and you do the matrix algebra, and this is what you get. Okay. Each new vector uses the entire previous one. You know what? I'm going to do this in Colab because a lot of these guys are actually running. Okay, so click, if you didn't see what I just did there, click the rocket ship and go to Colab. And we're working on getting it into a more interactive form. Okay, so that whole matrix equation is encapsulated in here. Note that it's a loop. Loops and NumPy, bad. We're going with it anyway. Pedagogically, yes. Run anyway. Come on. Okay, now we're going to define our matrix. Matrix A, we've got our solution, we've got our constant vector there. Typically, your initial guess for a linear solver, the most common one is 0. You just assume that your initial guess is the 0 vector. There's a good reason for that. It factors into the Newton method. We'll talk about that when we get to it. Trust me, guy, 0 is a good initial guess. Okay, we're going to solve this linear system because in here, this actually comes down to a matrix equation that we can solve for. We just invert this guy. Right, and after a couple residuals, first of all, we start with 0, 0. We get a residual that looks like that. This is the code. It's pretty readable, to be honest, right? We repeat it again. Now we get a different vector after cycling through 2 elements. That's our residual, right? And if you just keep repeating that, eventually you're going to get to this. Jacobi iterations are guaranteed to converge. Very desirable property of this. They will work if your matrix is diagonally dominant. Okay? Who remembers what diagonal dominance is? Bingo. Absolutely. Absolutely. And if you look at this at the update equation and noting that your diagonal term is here, right? And you kind of squint your eyes and you shake your head a little bit, you can start to imagine why that property is useful, right? This is going to be your largest term by definition in that row. So by dividing through by this diagonal term, your update is going to be smaller than everything else, than the other factors from your row. And what that means is that you're taking small, careful steps. As long as you take, like baby steps, you're walking on ice, you don't want to land on your nose, right? You take little steps and you're going to get there. It's going to take you a long time, right? Doing this. And the smaller your step, the more stable you are. But you are going to get there eventually. All right. Gauss-Seidel. So important. The way Jacobi works is that you are taking your entire previous vector and you make this one consistent with these two. Then you make this one consistent with these two, then this one consistent with these two, and then you update the entire vector. You don't modify it in place. That makes sense. So you do that scheme, you do that update scheme for every one of those elements, and then you update it. And what that means is that you can parallelize. You can have 5 different computers working on updating this guy, and this guy, and this guy, and the 4th, and the 5th, so on and so forth. And that distributes nicely. Yeah. Please. Not the same value. I mean that it would solve. It is the elements, when you plug them into this part, into this vector, it works. Yes. It works together because all of the elements have to work together. Yeah. Okay. The alternative to doing this one update is kind of obvious, right? And that's update as you go. So you're going to update this guy. You're going to calculate this new value based on these two. And this new value is going to become 2. Then you're going to calculate this value based on these two. And this guy is going to become 0.9. And then you're going to update this guy based on these two. And this guy is going to become, I don't know, 2.1. Something like that, right? And then you just go through and through and through. That's called Gauss-Seidel iterations. Literally, the only difference is that you update as you go, which also means that you're updating in place. With Jacobi, you have to build a new vector, and then that becomes your next guy. With Gauss-Seidel, you just say, well, this one is now this. This one is now this. This one is now this. It actually works out to converge faster. Almost always, and I think that's actually by definition, Gauss-Seidel will always converge faster. But if you were splitting this up amongst different groups, when you solve for the first element, you would have to say, hey guys, a new number is 2. Then you guys would solve and you would say, hey, I got 1.1. Then you guys would have, and obviously that's going to be a lot slower, right? So here's the problem with complexity and scaling and all that funny business now, right? It's not just about better algorithms and faster algorithm convergence. It's about how you can distribute that. Okay, I got to pick up the pace a little bit here. Okay, you go through, you work out the math. It works out something like this, right? And now when you do that, you're going to get, well, actually kind of a similar solution because you've only actually done 2 iterations. I'll show you the good stuff at the end here. Okay, one last thing you can do. You can also modify Gauss-Seidel. And you can say, start taking that step. But we're going to mix. We're going to accelerate it. We're going to mix the previous guess and the current guess. We're going to take whatever that distance was and multiply it by 1.5. So this is the idea, right? That you're moving in the right direction and you're taking a little bit of a larger step. It turns out that there's actually a formula for the optimal step that you can take. It's this. If omega here is 1, then you are exactly recovering Gauss-Seidel. So this is called successive over relaxation, right? Which is a fancy way to say that step that you're taking, you are doing a larger step. You are over relaxing it. You are relaxing towards a solution, but you're taking a larger step than you otherwise would have. And for this optimal value. If the omega is less than 1, then you are forcing it to take smaller steps. You are under relaxing. It'll be more robust, and it'll take longer, but hopefully it'll be a bit more robust. Similarly, for larger than 1, you're going to overlap. You're going to relax faster. Okay. In general, for a well-chosen omega, you're going to get better, but the magic is how you're going to do that. There is an optimal form here. I'm going to show you this guy, right? And sure enough, you have, again, done 2 iterations, so it's not actually helpful. Let's move on to the one that it is helpful. Okay, summary and comparison. I'm not going to rush this. I think I'm going to come back to this on Thursday. I'm going to go through the summary. I'll show you guys the demonstrations, but then I'm going to circle back on Thursday, and I'm going to start with going through these iterations again before moving into the Krylov subspace. Okay, Jacobi, Gauss-Seidel, SOR. They're all very suitable for large, sparse matrices. They're all very good. None of them are implemented nowadays. They've all been, they're effectively obsolete. To be entirely frank, by Krylov, it's a lot more powerful. However, you will still encounter SORs, right? Successive over relaxation. Keep it in the back of the mind that that's Gauss-Seidel. What does that mean? Look up the textbook. Oh yeah, that's what it means. It's on Wikipedia anyway. Since when you rip that matrix apart, since the matrix doesn't change, it's a stationary matrix, you don't have to update it. You just keep applying that over and over and over again. A lot of those terms can be pre-computed within the loop. There's a lot of simplifications that you can do for that, and that makes it a whole lot faster. Is guaranteed to converge for diagonal dominant matrices and symmetric positive definite. So again, symmetric is obvious. Positive definite isn't so obvious. We're going to talk about that with conjugate gradient on Thursday. Jacobi parallelizes very well, but converges slowly. Gauss-Seidel converges faster, but doesn't parallelize as well. SOR is a more general case of Gauss-Seidel, might converge, blah, blah, blah. Okay. If you want to get ahead of things, start from the last section here. You have to run the entire notebook, so it's going to use all those functions. It's going to build those, and we're going to do a bunch of case studies going all the way up to, I think, a 5,000 matrix. N is 5,000. Spoiler alert, we're going to start off with Jacobi iteration. It's going to go terribly. We're going to abandon it, and we're just going to go with Gauss-Seidel. And I think even the LU solves. Oh, the LU solve didn't take so long. 3 seconds versus 800 milliseconds. Okay. See you on Thursday. Reminder that my office hours are Thursday at, I think, 1 until 3. In my office, NRB B120. It's beside the garbage cans. Make of that what you will. Back to stationary methods. So we're talking about iterative, i.e. indirect methods of finding the solution, a solution to a linear system. Let's see. I'm just going to run this entirely. Yes. Run all. Okay. We talked about Jacobi iterations. And Jacobi, basically, you're making every element in your vector consistent with all your other ones. Actually, both Jacobi and Gauss-Seidel. You're doing that. But in Jacobi, you're not updating as you go. You take your initial guess, you make this one consistent, this one, this one, this one, this one. So it lends itself to this parallelization, this distribution and parallelization. As opposed to Gauss-Seidel, where you, did I actually turn this thing? Well, it's too late now. As opposed to Gauss-Seidel, where you're updating as you're going. So you're already using your previous answer in your current answer. Converges faster, but now you're communicating, right? That group, you figured out a number, now you need to shout it, and this group over here needs to get it. And then it makes it a serial process instead of a parallel process. Yeah.
To check, like the Jacobi and Gauss-Seidel, you can use that as like preconditioners.
Ooh.
Yeah.
Preconditioners is tomorrow.
Okay.
Yeah, don't get ahead.
Okay.
But yes.
That's because it's on the assignment.
Yes, you can, yes. Okay, and then you have SOR. SOR is what you're actually going to see. I haven't seen anybody doing block Jacobi. It's not really the same thing. Okay, we'll talk about that one a bit more tomorrow. SOR, you are probably going to see even console has SOR in it. SOR is a generalization of Gauss-Seidel. So SOR has this fancy parameter omega. When omega is equal to 1, omega is kind of the relaxation parameter, right? So you have a guess of the direction you're going. You can either keep that guess, in which case you're Gauss-Seidel, or you can accelerate it. You could take 1.5, and maybe you've gotten faster. You could take 0.5, and now you're going slower, but you're a bit more robust. So it's just an easy way to do that. And there is theory about what the optimal guess is, which is kind of nice, right? It's one of these things. It's good to know that there is a theory for what it actually is. So to your point about what you would actually need to know for this course, I will not be asking you what this formula is. This formula I consider to be a parameter, right? What the difference between SOR and Jacobi is fair game, right? What the difference between SOR and Gauss-Seidel is a nasty fair game, but it's still fair game, right? Why this is a 1 and not a -1, I don't care. I don't even know. I'd have to go through the math too. Like this is Wikipedia stuff. Okay. Summary and comparison. All of them are suitable for large sparse matrices. Sparse in particular because it is an element by element approach. It lends itself to this sparsity structure. You can imagine extracting one row and now you only have 3 elements instead of 150 million. They are called stationary methods because you take your original matrix, you rip it apart, no decomposition, you just pull it, right? And then you get this decomposition, this lower triangular, diagonal, upper triangular, not the same as LU. Again, I apologize, but they don't change. That's the stationary part. And you just keep doing that over and over and over and over and over again until your answer is good enough. They are generally more efficient and faster. Convergence is not guaranteed in except in the case of Here's somebody. And ask the back row. Telling you right now.
Diagonally dominant.
Yes. Diagonal dominance. This is where, and if you look at that update equation, you can kind of see like some indications of why that diagonal dominance is in there. Gauss-Seidel and SOR for super extra bonus points with sparkles on top. When is Gauss-Seidel and SOR convergent? On top of, guaranteed to be convergent, on top of diagonal dominant. Not you, you already answered. Anybody else want to take a stab? Yes. SPD. Matrices that are SPD are nice matrices to have. We're going to talk about what the heck SPD actually means. I don't understand what it means if somebody tells me, well, X transpose is greater than 0. What the heck does that mean? It means it's a bowl. That's what it means. It means that it's a convex shape. It's like a parabola that's up in all directions. If it, I'm getting ahead of myself. Talk about that in a minute. Okay. Shared guaranteed convergence when Gauss-Seidel is between, when omega is between 0 and 2. Great. Okay. Will iterative solvers always be faster? Wall time faster? Even if it does converge, will it be faster? Not necessarily. Is there any way to tell when they're going to be faster? No, you're screwed. Except in very, very specific, specially engineered cases. Your luck is in the wind. Okay, so what we're going to do. So I have some rough tools. I got to speed this up because we're not even on to today's lecture yet. We're going to code it. The Python standard libraries don't even have an implementation of these things. That's how, like, kind of not obsolete, but historical. Let's go with. Okay, we're going to start with a guess. We're going to start with A and a vector B to solve it. We're going to do something using A and B, and then we're going to check how well the guess solves the linear system, and we're going to repeat. Okay, so this is my nice cooked up example. Let's see. Right. So what we're doing here is we're calculating. Okay, so that's just showing where the things are. Here's our matrix A, B, X naught. All this is on the notes. If you go to the rocket ship icon, I do need to skim this part because we're out of time a little bit. But you can run it for yourself, right? This is just calculating that. We're plotting. Here we're actually doing the plot. Okay, so what this is, we're starting with a guess. Typically, this guess is going to be 0, 0. There's a reason. It's to do with Newton's method, nonlinear part. Talk about that either next week or the week after in root finding. Right, and then we're going to change, and we're going to go through and we're going to update our guess. This one is for iterative, for Jacobi. Okay, so this is our original guess. Right, jumps over here for the next guess. Next guess, up. And in we go. It takes 12. That's our true answer. This is our residual. You can see how the residual is dropping. And this residual, I think this is the absolute residual value, is small, right? Anything below 1e6 is kind of small, is generally considered small. Okay, if you go back here and you change this guy, right? This is one of those things that hopefully will change, right? So now we're using the Gauss-Seidel step. Rerun that block, and now we get the answer in 6, which is a dramatic improvement, right? And you can see that the path here has changed. We've gone 1, 2, 3, 4, 5, 6, and we're here. Yep. Yeah, I probably shouldn't have showed it like this, should I? This is technically it is the slope. These contours are are actually the residual of AX is equal to B. So AX minus B is what these contours are. Oh. In some cases, that is a bowl. And we'll talk about those cases in a second on the next slide. Yeah, I should have, but no, this is the residual. That's what these contours are in. Yeah. Now, comment that guy out, enable the SOR step, and you converge in 5. And it goes boom, 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 and you're there. Let's see the value. This is creating a diagonally dominant matrix, right? You can read through all this stuff. Exercise for the student. Okay, we put in the iterative solve, and here we go. So for a system size, that is n is equal to 4, four-dimensional, you have 4 unknowns. Let's solve it. It gets the answer in, oops, is this working? Oh, here you go. Okay, so the LU solves takes 72 microseconds. Jacobi takes more. Takes longer, right? 1 millisecond. Gauss-Seidel is 300 microseconds. It's still more than LU, right? SOR is even longer. It's even longer than Gauss-Seidel. Professor, what the hell did you do to us? Right? N is equal to 4 is small. You're never going to see N is equal to 4. You're going to start with N is equal to 100. So now you've got 100 unknowns. LU takes 271 micro. Jacobi still takes more, 331. Gauss-Seidel takes even more. Oh my God, right? And SOR even more than that. Guess what? 100 is still small. This guy actually had such bad Jacobi performance that it clocked out, and I had to disable it. Otherwise, we would still be waiting for it to solve, right? LU for 1,000 by 1,000, 35 milliseconds. Gauss-Seidel still takes longer. We still haven't even gotten to the good part. 3,000. Let's run this one. Now we're starting to see payoff. LU, 700 milliseconds. Gauss-Seidel, 360. This is all running. This isn't pre-programmed. This is executing right now. And if you run it again, you're going to get a different answer because it's all randomized in the beginning. Okay, 5,000 by 5,000. 5,000 unknowns. Here we go. Now we're getting some interesting things. 3.4 seconds versus 830. Right? And if you go up, should we do 10,000? You aren't able, you can edit this, but you aren't able to save over it, so go nuts. You can always just reload it. Right? So now we're doing 10,000. How does LU scale? Somebody? This is an important one. What does LU scale as with N? Exponential? Almost. Somebody want to jump in?
It starts with n cubed and continues with n squared because back substitution forward.
Yes. But the decomposition itself still takes n cubed. So if you're only doing that calculation once, then it's n cubed. But if you're doing it repeated times, then it can be the n squared. Yeah. Note that this is not sparse. This is a dense matrix. So it is actually n cubed. And if you just played around with these n's, you would see that cubic behavior. Okay. So here, LU took 23 seconds. Gauss-Seidel took 3.43. If you looked, for example, and you used the time it function on these examples in order to get some data about how long these things are taking, you would see approximately n cubed growth on the LU. Gauss-Seidel, I'm not actually sure off the top of my head. It depends on what's going on in your matrix too, right? But you would see very different scaling. Time it is not the correct way to do convergence or to do computational complexity or efficiency, but it's a convenient way. Because otherwise you got to do all the math and do all the crunching, and ain't nobody got time for that. Yeah. Yep.
For large matrices, the n cubed is dominant and the n squared. Okay.
No, you're talking about the LU and then back substitution. So when you're doing LU and then back substitution, the decomposition forming the lower and upper matrices in the first place takes n cubed. But then once you have those matrices, then passing through and actually solving your system happens in n squared, right? But the decomposition, if you're only solving the system once, it's still n cubed. So it's still terrible. Right? The whole reason that you would have those matrices. So the other thing about that is if the full matrix is sparse, is banded, then the L and U maintain that sparsity pattern. Right? So the storage of L and U is also efficient. That's why you wouldn't just solve it once. You would do that, and that's kind of become the standard approach. But make no mistake, LU is n cubed. And if anybody ever asks you why you don't use LU, you say it's n cubed for dense matrices. The n squared part is just kind of like an aside that if you repeated the calculation, then you would do something else. But really, it's n cubed, and you should consider it n cubed. If it is sparse, is LU better or worse? It's a little bit of a trick question. Hopefully you guys got it at this point. You can give the standard LU solver a sparse matrix, and it will solve in the exact same amount of time as it would with a dense matrix, because you haven't fed it into the sparse part. There is a dedicated sparse matrix solver that is dramatically faster. And that actually turns into something approximate. I think it's approximately linear. Something like that. It has to do with the bandwidth and the sparsity, right? And it's very, very useful. It's very, very important. Yeah, like all like COMSOL and PETSI and FireDrake and Phoenix and all that stuff, like everybody like relies on these things. All right. We've got 10 minutes left for today's lecture. We're not going to cover it. How long is Preconditioners? Oh man, that's a long one. All right. Whatever. At least there's a nice picture there. All right. Tomorrow might be a quick class. Forewarned. All right. Krylov subspace methods are the current de facto standard. They are different from the stationary methods. So the stationary methods, what we tried to do was you take a guess and you go either kind of element by element, or conceptually you go element by element, and you keep doing the same thing over and over and over again until you get to a solution. Okay, Krylov subspace methods work on the idea that we're going to build a basis for your solution vector. Who here remembers what a basis is in linear algebra? Okay, show of hands. I won't ask you what it is, just show of hands so you have a rough idea what a basis is. Okay, so, right? Understandable, completely understandable. Did I bring my marker?
It's a set of vectors that can create the whole subspace.
Effectively, yes, right? Graphically, right, you have y hat. I learned with y hats. I don't know what you guys learned with, right? X hat, and a point over here is what? 1, 2, 3, 3, x. This is 1, 2, right? 3x, 2y, right? Could I have another vector basis that looked like this? Is this a valid vector basis? Yes, right? No problem. What about this? Yes, right? The 50-cent question, what about this? Or this? No. Why? You got it. Guess what? If you try and transform something in this to a coordinate system like that, you're going to get a singular matrix. That's what singularity means. It means linear dependence. It's all related, right? Okay. What is the best? Yes. Why?
Because it's like, you know, it's like, you know, it's obvious. I don't even have to say.
I need this is math, man. You already answered questions. Somebody from over here, unless somebody wants to raise their hand. You guys, you already answered. Okay, looking at the back, 1, 2, 3, 4, 5. Any of you guys? Why is orthogonal vector basis convenient? It's not different, right? All vector bases are equivalent. What makes orthogonality beneficial? Why do we want it? In the back. Take a guess. Independence, yes, right? Actually, I would say that's it. That's the exact answer, right? Whatever, if you wanted to find out what this point was on this guy, all you would have to do is project this onto this. It's a dot product. It's super easy. And whatever you got on this guy is independent from what you would get on this one. This is the heart of the conjugate gradient method. Okay, this is what we're about to talk about It's going to be super confusing, and hopefully by tomorrow it will have settled and we can move on. Okay. So we are building. So in 2D, this is easy, right? In 2D, 2 dimensions, how many basis vectors do you need to describe the entire thing? 2, right? How many vectors would you need to identify where this point was? What's the minimum number? If you didn't care about anything else in the space. If you magically found the basis that exactly points in that direction, all you're doing is finding a scalar multiple. Technically, that's an eigenvector, but that might just be too much. That's what actually eigenvectors are. They're a linear basis. We won't talk about that. Right? So technically, you only actually need 1. But in fairness, you're never going to find that 1, so you're going to need 2, and then you can describe the entire space. Right? So what that means is that for an n-dimensional problem, you need at most n basis vectors. But generally speaking, if you're doing something halfway intelligent, you're going to need a lot less. And that's the magic. That's why these things are like the go-to for it, right? It's like Taylor expansion, kind of. It's not like Taylor expansion. Let's not go there. It's an expansion. It's a series expansion. There we go, right? You're ideally, if you do this well, you're going to find the dominant vectors. You're going to find more and more of the dominant vectors until you don't care about the rest. Because you know there's exactly one solution. So if you find a solution, it is the solution, and you can go home. Yeah. Conjugate gradient is a standard tool for solving symmetric, positive, definite systems. Where were we talking about SPD? Did you guys? Yeah. Okay. What the hell is a symmetric, positive, definite matrix? There's a technical definition. It goes something like X, A, xt greater than, strictly symmetric positive definite is xa xt always greater than 0. Positive definite just means that that's greater than or equal. Okay, so everybody understands that and we can go away, right? I never understood a damn thing. What it means is that if you had a quadratic surface, like a bowl, right? That matrix is the second derivative of it. It's called the Hessian. And if you have a surface at all, any kind of surface, then you can write out an equation like this, right? Everybody understand how that one works? So you take your linear system, AX is equal to B. If you have a symmetric matrix, I'm going to come to this one in a second, you can say that you have this associated function, which is quadratic, 1/2 a xt a, see I got the t in the wrong place, right? Minus btx. If you take the derivative of that, right, you're going to get our good old ax minus b. That's the linear system. This only works for symmetric matrices. And the reason it only works for symmetric matrices is because you need to have die f by die x, what is it? Die y is equal to die f by die y die x. So if you have this function f, you know this, like this law of mix, this is the field law, right? You know that this has to be true. And your A matrix becomes the Hessian, the second derivative. That's what this is, right? This looks terrible. It's actually super obvious, right? This is the second derivative of x with x1, whatever your coordinate is. This is the mixed, more mixed, the last one. You go down, you go around. If your linear system can be associated with a surface, right, then you know that the Hessian is symmetric. Only symmetric, not positive definite. Right, Hessian positive definite, blah, 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 blah. Okay. When it is positive, you will have a surface like a bowl, right? Something that looks like this. I should have a nice 3D picture. If you don't, I don't have a convenient picture, so I'll just Google it. Radix saddle surface. You are going to have a surface that looks like a saddle. And it's actually called a saddle point problem. And the problem with a saddle point is you do actually have a system. There is actually a point here where AX is equal to B. But it's not a minimum. It's a saddle point. And that's because you have, it's an extremum, right? The difference between minimum, maximum, and extremum, right? A saddle point is so if the thing isn't symmetric, positive, definite, technically you have a point which is both a minimum in this direction and a maximum in that direction. That's the monkey wrench that throws all this stuff off. Yeah.
That's the problem.
There is no global minimum. For this, there is no minimum here. You would just keep falling, right? And unfortunately for us, the natural world is generally speaking a saddle point problem, which causes all kinds of problems for optimization methods, right? Because we're actually interested in this point, but we can't get it because it keeps falling down. Okay, I got 2 minutes. I'm going to try and use them. Okay, just for reference, the other type of second derivative function that you're going to encounter is called the Laplacian, right? Hessian is just kind of like you're filling out this matrix, right? You're just doing all the derivatives. You're not doing any cancellation. In contrast, your Laplacian, which is all over console, computational multiphysics, right, is you're summing those diagonals. So some people actually define the Laplacian as the sum of the diagonal of the Hessian, which is an overly complicated. People like to right. Here's the magic. I'm going to come back to this tomorrow. I'm going to be repeating this exact line. Starting at a point X, this is our initial guess. We're going to choose a step direction. So imagine yourself on the surface. We're going to start at a point. We're going to choose a direction, and we're going to go as far as we can downhill. How do you find as far as you can downhill? Somebody give me an answer. We got JC or one of them, so 3 people at the back. How would you go downhill? If you were standing on a hill, how would you go downhill? Come on, one of you guys. Starts with a G, ends with a gravity. Right? You're just going to fall down the hill, right? In mathematically, what you're going to do is choose your direction and go and optimize that. And you're going to keep going down until the first derivative is 0. Right? If you crunch through the math, right? So you're going to start at this. Your next guess is going to be that plus your optimal step length in a certain direction. You're going to go down. Here you can calculate what your actual thing is. The question and the magic comes into how you choose your direction. I'm at the end of the time, so give me like 30 seconds more. How you choose your direction is the magic. You would be tempted to go downhill. Turns out when you do that, you can look at it and it's going to do something like this. This is called gradient descent. You are literally falling down the hill. And this is not the right answer for this type of systems. It is for GMRes. It's not for this one. The magic here is that you end up zigzagging things. And you're going to see tomorrow, spoiler alert and cliffhanger, the magic comes down to finding independent vectors. That's where we're going with this. See you guys tomorrow.
Yeah. Another question about the assignments.
Please.
I know you mentioned when we talked about the first name, like in the lecture here.
Talking about Krylov subspace methods. So if you remember, when we have an equation that looks like AX is equal to B, right? We can imagine that that could be like the first derivative basically of some quadratic surface, right? And then AX equals B is like the extremum point. Hopefully it's an optimum, then things become easier, but otherwise it's technically it's an extremum. That's not always the case. It requires A to be symmetric. That's because of the mixed derivatives fact. But when that happens, then we can kind of conceptualize this thing a bit easier. Okay. So if the surface has a minimum at 0, right? And then because of this equation, it becomes AX minus B. That's our residual, right? This is the Hessian. This is how we derive, like from that surface, what A takes the place of. Blah, blah, blah. It has to be symmetric. And again, if it is positive definite, then it is concave. right, then it's a bowl as opposed to a saddle or a downward facing bowl. Saddle point problems are the hard one. Okay, so the algorithm for finding this thing is that we start at some initial guess, typically 0, doesn't have to be, right? We choose a direction and then we optimize by the step length. Because we have a relatively simple equation, we put that in here and we can just calculate the optimum value by just saying, okay, when does df by parameter step length alpha, right, become 0? That's our new minimum, and we go in that direction. So the magic to this is how we determine the step direction. Oh, sweet coffee. It's a coffee day today. Okay. Intuitively, if we're on a hill and we want to find the bottom of the hill, we follow gravity, right? We just roll downhill. That's called steepest descent. It's literally the steepest descent. You follow the negative gradient. That's a perfectly good way to do that. If you do that, you find that it becomes that. It actually becomes negative of your residual. Because your residual is related to the gradient of that surface, that's ax minus b. So that actually just works out to be your residual. Very convenient. And solving for the optimal step length. You guys can see that, eh? You can always zoom in here if needed. Also becomes like super trivial. So you get a really nice clean equation. And then if you, so if you are going to run this, put it into Colab and run it through there. This, the GitHub hosting page is static. It doesn't have a runtime underneath it. Okay, but the Colab should all work, right? You can go through the algorithm. Basically, what you're doing is you're finding your initial guess, you're calculating your current gradient, and you're finding the optimal step length down that gradient. What you get, and you plot it, is something that looks like this. This is our initial guess, 0, 0. You take the first step, second step, third step, fourth step, fifth step, sixth step, right? These contour lines are your residuals, technically, which is not the same as the height of your bowl, right? It's the gradient, not the height. But that's a little bit of a point that's more of a subtle one, not so necessary. Okay. Anybody see the problem with this? Nobody? Nobody? Class? Anybody? No? Okay. So first of all, what is the dimensionality of this problem? This should be super easy, guys. Anybody want to flash some gang signs or something? No? Hands? What's that? Your search space is 2. Your search space is X and Y, and the vertical axis are close. The vertical is your your residual or your height, right? Technically, the magnitude of your residual or your height. Okay. Remember that the whole idea of the Krylov subspace methods is to work out a vector basis, right? And not surprisingly, the vector basis, so the way that you get from here to your final answer is you have to sum, right? This took 9 iterations, and you have to sum through all of your steps. So you start off with x naught, you go alpha 1 in the S1 direction, alpha 2 in the S2 direction, alpha 3, alpha 4, 5, 6, 7, 8, 9. Okay? You're in 2 dimensions, but this is coming out with 9 vectors that it has to go through. 9. Anybody see that as a problem? You have too many, right? It's a 2-dimensional problem, right? You could. Right? Coming back to the idea of mapping out a point, right? Normally, you would do something like this, x, y. You could have something else like this, and you could have another vector like this, and you could have another like this, and another one like that, and another one like that, and eventually you would get to that. But it's wasteful. You're taking more steps than you have to. Why? Not you answered. Guys, if ever like I start asking questions, volunteer for the first one because the first one is the easy one. The latter ones are the harder ones. And if I pick on you for a latter one, you're going to be scratching your head. Okay. Why? looking in the back corner here. Why is it wasteful? Person over there who's not there today actually had the answer, but yeah. Oh, okay. So you could do if you knew that vector, or if you just like randomly, you managed to pick this vector and this is your solution over here, your optimum, that optimum step length would drop you straight there and you would be done. You would walk away clean in exactly one step. The problem is that you'll never actually, like, you're just never going to find that one step, right? First of all, what is the maximum number of vectors of independent bases that you would need in 2D, right? So why do we have 9? What are the latter 7 doing? Yeah, but we only need 2 because we're in 2 dimensions. So why do we? What are the other 7 doing? They're overcorrecting, but they're also overlapping, right? They're going through, and you can see like these guys are not all independent. They're linearly dependent, right? Because they're going over and they're going back and forth and back and forth. So, okay. What could we do about it? The problem is overlapping. The correct mathematical term for something that is not overlapping is, you answered. Back corner, back row, you two. I'm just going to start moving up row by row. What's the term for 2 vectors that don't overlap? I see hands going up. Parallel? Exactly the opposite. What's the opposite of parallel? Orthogonal, right? What you could do, right? So here's the magic. Steepest descent is nice because you don't need any memory. All you're doing is you're just taking a step, and the next direction, right here, you take one step, and the next direction just goes downhill. Well, that way, right? It doesn't know anything about this step. It doesn't care anything about that step. This one just goes downhill. And again, it's forgotten that it actually already took a massive step that way, right? One way that we can help with this is to introduce a memory, thereby making, so one option is to make each subsequent vector orthogonal. There's a problem with that. It doesn't actually work that way. At least it'll help with the overlapping, but it doesn't actually solve it. Right. Instead, what we need to do is something called the conjugate gradient. Okay. The magic is, so what we're trying to do with all this stuff. Can you guys see this? Should I turn on lights? You guys can see? Yeah. So what we're trying to do is we're saying A times something, which is x naught plus alpha 1 S1 plus alpha 2 S2 equals B. Yeah.
Sorry, could you turn the light on?
Yeah. Better? Yep. So this is what we're trying to do, and this is the idea of the Krylov subspace method. We're trying to build a basis for our solution X. And we're trying to build it based on like careful choice of these steps. The way the conjugate gradient works is that we want to make sure that whatever path we're choosing, here's the trick, right? It's not that these vectors, these guys, are going to be orthogonal. What we want to make sure is that the resulting B, change in B, is orthogonal. which is to say, what we need is, so this is a constant, right? So this comes out front. Alpha 1 A S1 plus alpha 2 A S2 dot 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 dot, right? You want these guys to be orthogonal. Does that make sense? Yeah. This is the heart of the conjugate gradient. Conjugate gradient is something that you guys will encounter. It's a standard tool. A lot of people use it. Whenever you can use conjugate gradient, symmetric positive definite matrices, use conjugate gradient. It is quantifiably better than your alternatives. Yeah. Aha, each other. Each other. Correct. Correct. How do you write that algebraically? Dot product? Okay. Let's say you said dot product. The answer is dot product. Right? So what you want is, so you want each of these guys to be orthogonal to each other, right? There's another way to think about it, which is in terms of correction to B. It's like the error correction and what the components of the error correction. I found that too complicated. So this way is a lot easier, in my opinion. What you want is this vector, right? Matrix vector is a vector. So you want this guy dot this guy equal to okay. When, sorry, this is at an angle. You guys just tilt your head. When can this guy be zero? This involves like multiple matrix products, right? Matrix products bad. Too complicated for us. When can this guy ever be zero? Can you guys see this back? Yeah. I'm going to give me a simpler form of that. That would guarantee it be zero. I'm going to go for this bubble right here. How about 1, 2, 3 from the back? Pink water bottle, Lululemon. Nothing? All right. Let me give you an analogous one. Let's say if you had pi a b equals 0. When would this equation? What's the condition for this guy to be 0? Pi is just a constant, doesn't mean anything. You need pi? Yeah, just a constant, right? Cancels, and you just have a dot b is equal to 0, right? In order for this guy to be 0. What's that? Yes. No. So one of the conditions for, it's kind of a hidden condition, symmetric positive definite implies invertible, which is not a trivial thing to understand. Trust me, it implies invertible. So because it's the zero matrix, not quite, it's actually the null vector. This guy has to be the null vector, 0. Right? So because A in general, A times a vector is going to be non-zero. Right? Unless that vector is 0. It's the same with a constant, the same with like vanilla algebra, right? So the only way that A times all this stuff is going to be 0 is if this guy is 0. And this is a lot easier to enforce because you've dropped one of your matrix products. And this is how you get the conjugate gradient method. So what you want to do here is you're going to make the next step not interfere with the previous one. And they're going to be orthogonal when multiplied by 8. Mathematical term for it is, what is it? I think they call it orthogonal in A, right? You want S2 and S1 to be orthogonal in A, which doesn't mean anything unless you're a math major. But if you're a math major, then it'll mean something to you, I suppose, according to Wikipedia anyway. Okay, so what you want to do is you want to say that, let's see. So we're going to base the next step on the previous step and the gradient descent. So we're still using the information of where the downhill is, but now we're also going to, right? And that we showed that the gradient was the residual, right? And now we're going to change the next step to also be a conjugate to the previous one. Yeah.
There can only be enough two vectors. And just
You're jumping ahead. Don't skip ahead. I'm building to something here. Right? So you want this to be true, and you're going to require that these guys are conjugate to each other in A. What does that mean? It means this. It doesn't mean that these two guys are orthogonal. Right? That's the catch. These two things are not orthogonal, but their effect on the solution, that being through this transformation A, that's the orthogonal part. When you do that, you can solve it. You can find your step length. You can calculate through your step direction, right? Do the math. It's actually pretty easy math. And we're actually going to make the new step conjugate to all the previous steps. When we do that, here's a true answer. Let's run the thing, and we get it in precisely 2 steps. Some people say that this actually makes the conjugate gradient method a direct method because you are guaranteed to get the solution in at most n steps, right? Which is kind of like the definition of one of these direct methods. Typically, right? And the engineers would say, well, actually, you don't typically need like n directions. You can typically get away with much, much less. So I've seen conjugate gradient methods converge on matrices of like n is 100,000, I think was the largest I saw. And it converged within like 3 or 4 steps, right? Which is a massive benefit. Huge, huge, huge. Sparse thing. Okay. What was I going for here? Right? If you don't believe me about the conjugacy, you can just calculate and you can follow through those steps. You do the dot product, right? And sure enough, yes, it does equal machine 0. What is machine 0? Blah, blah, blah. Anything e to the minus 16. E to the minus 16 is like the decimal equivalent of binary to the power of double precision, right? Anything below E1 minus 16 is, or around E1 minus 16 is effectively machine 0. Okay. You can also find, by the way, that the residual at each step is also orthogonal, which if that helps you sleep at night, great. It doesn't really have much meaning to this course ending. Okay. Where are we going for here? Right. So method of steepest descent doesn't enforce all the vector bases. Sorry. Method of steepest descent doesn't say anything about the previous steps, right? You're just going downhill. That turns out to be inefficient because you end up undoing some of the previous steps and you get 9 instead of 2, right? Conjugate gradient method does enforce that conjugacy, and therefore you get a necessarily required convergence in at most whatever the dimensionality of your problem is. But it relies on A being symmetric positive definite. Okay, just as a quick aside, because we're going to get into it in a second with preconditioners. Should have already gotten into it. I'm late. There is an interesting artifact. It's not really an artifact. It's a mathematical fact that we don't technically need the matrix A at all. Because what we are only actually interested in is A applied to some vector. So technically, we don't need to store the matrix A. We talked about like efficiently storing it, sparse matrices, whatever. But mathematically, when we actually implement this, all we actually care about is the action of A on a vector. If you have some other way to calculate that action, right? That matrix vector product. If you could calculate that matrix vector product without calculating that matrix, and you have surprisingly a lot of ways, right? You think like, well, how the hell would that work? But trust me, there are actually a lot of ways that you would get that fact. You can use something called matrix-free methods. And matrix-free methods are almost exactly the same, but you'd never need to store A. So it's kind of like a computational thing. A lot of the preconditioners actually use matrix-free methods. The IOU preconditioner, we should have already gotten to at this point, uses that as an operator, but I'm just telling you that here. Okay. Yeah, okay, so CG sometimes is called that. Now, there is one insidious problem with this. When we build up our vector basis, we're making each vector orthogonal or conjugate, right, to the previous directions. That would work, and that would work great if we had those previous directions exactly. But we don't have the previous directions exactly because of round-off error. And a little bit of round-off can accumulate. And if you base one off the previous one, guess what? You've just compounded that uncertainty. And now you do another one and you've compounded that. And once you get up to like 100 steps, something like this, you're just building up that uncertainty and uncertainty and uncertainty. So a lot of these methods have a restart parameter. And restart is literally, all right, that's enough, kill it, start over again. Every once in a while, you'll run into something like that. And if you're ever looking at like PETC output or even COMSOL output, you'll see like the residual take a massive jump, typically around like some multiple of 30 in the iterations. That's your restart, right? Typically, they like to keep it around 30. That's the magic number that people use for that. Okay, all this worked for symmetric positive definite matrices. Use conjugate gradient. It is the best. When you have it, use it. If you don't have it, if your matrix is not symmetric or is symmetric but isn't positive definite, you have to fall back on GMRes. GMRes is the workhorse. When you have CG, use it. When you don't, you're going to be using GMRes. I don't know if I just like pronounce it that way or other people do too, but okay, we can adapt the basic method, and I'm going to go through this super quick. The idea is that we're going to construct our vector basis, basically making these guys orthogonal, not conjugate. We're just going to make these guys orthogonal. And that's it. That's all we can do. The conjugacy breaks down without the framework of this symmetric positive definite. Typically, so what this does is it makes each successive step in this series at least at least independent. They are linearly independent of each other, which helps a little bit. Typically, these things will converge in at most n parameters, but it's not nearly as robust as conjugate gradient. I don't think convergence is even guaranteed. Conjugate gradient is super strong, is super robust. Okay. Here are some examples, and it takes longer. Any questions, or can I jump on to the next one? So, okay, so frame of reference, just put that into place for this course. I'm not going to ask you to program conjugate gradient. I'm not going to ask you to program GMRes. Both of these are actually in SciPy because they're actually used right now, right? COMSOL is using GMRes and conjugate gradient under the hood. Those are its go-to things. What I want you guys to take away from that is symmetric positive definite. You use. I'm going to pretend everybody just shouted out conjugate gradient, right? Otherwise, what you want to use GMRes. The problem with GMRes is that it doesn't converge very robustly. So how do you make it converge more robustly? Glad you asked. Preconditioners. Okay, any questions on GMRes, conjugate gradient before I go on? Yeah. This guy?
Iteration, right?
Yes.
That go to this.
Correct.
Then we assume that it has no error, so that's the desired.
Ooh, it's not error, it's the residual. It is AX minus B. And you are, by definition, you are solved when it is equal to 0. Correct. Yes, yes. No residual error, just residual. Yes, yeah. Anybody else? Okay, preconditioners. Super late. Okay. Can we solve this? There are 2 lines. They're on top of each other. Can we solve it? I see shaking heads. No, right? Can we solve that? That's just a little bit off, right? Yes, we can. Analytically, direct methods, yes, we can. What do you think is going to happen with iterative methods? Right? I see some shaking heads. Yeah. You got it. It just kind of like flutters around there, right? And what that's going to translate to is in your iterative methods, it's just going to go like this, like this, like this, right? What is the best one? What is the best case that we can hope for, right? Survey says X. Ideally, what we would have is something like this, because these 2 lines are, there you go, thank you, right? Can we transform this nasty guy to something which is up? Right? How would we do that? Right? Always answer the early questions. The how is going to be coming later. How would we do that? Yes, were you going to say that? There you go. I'll ask you. That's what a preconditioner is, right? So instead of trying to do this nasty thing, what we're going to do is solve a related problem that looks better, right? And what does look better mean? It means that it behaves better. You're separating out those lines. This is just a coordinate transfer, right? This is what preconditioners are there for, but they also have another massive, massive benefit that we're going to get to in a second. Okay. Direct solvers typically do not need it because you're as close to analytical as you can get on a machine with machine precision. So you don't have to worry about it. That's why I said like console, use LU, use the mumps, Paradiso, all these other ones, super LU, like use that because that if there is an answer, that's going to find it, but it's going to kill your battery because it scales as n to a power. Worst case scenario, n cubed, practical, you know, like large, right? It's not going to work very well. Iterative solvers are better, they scale better, but there is no good preconditioning technique that works well in all cases. That's the caveat to that. So this is nice because it's like a 2-dimensional thing, and I can draw it on the board. Reality, when you get up to a 1,000,000-dimensional space, it becomes a lot more complicated, right? So we have to generalize this thing and just don't try and picture it too hard. Or if you do, like, you know, don't come to me when you're doing this. Okay, there is no general preconditioning technique that always works. Sometimes some preconditioners are better suited to certain types of physics, which motivates the idea of a physics-based preconditioner. But then there's a problem with how you combine 2 different types of physics, which is what you did all winter semester last year, right? Preconditioners are basically the active field in research in this area. All the major investments, so PETSI, the portable extensible toolkit for, I fail, I don't remember, compositional something, whatever. It's at the bottom. There's a link. That is a massive investment underway at Argonne National Laboratory in the US, right? They have a team of like 10, 15 people who are working on precisely preconditioners. They are basically the key to solving large linear systems. By large, I mean million plus, which is kind of when you get up to scale on these things. There are a very large variety of these things, and we're not going to cover most of them, to be entirely honest. I'm going to give you guys kind of like the bulletproof ones, and then it's up to you guys to look into the other ones. And by up to you guys, I mean if you end up doing a PhD in the field and you need specialized solvers for Navier-Stokes. Navier-Stokes has a preconditioner that is very well built for Navier-Stokes. Problem is, as soon as you combine it with some other type of physics, it falls on its face. Welcome to the game. Okay. So what we want to do is we want to multiply through by a matrix P inverse, right? Why am I using P inverse? There's a reason. It's to do with the matrix product. To make the system easier to solve, as long as P inverse isn't singular, right? Then the matrix won't change. Then the system won't change, which is to say, so singularity is all about your null spaces, right? As long as, if you didn't know that, singularity is all about your null spaces. So if you have this matrix transformation that transforms a vector to 0, you're screwed. Because if you try and take 0 and make something out of 0, it's not going to work. That's why you can't invert singular matrices. You can't invert matrices with a null space that includes more than the 0 vectors, the technical definition. Okay, which is also why I don't really want to get into pseudo-inverse, because pseudo-inverse has a lot of null spaces. All right. There are a couple of options. One is left preconditioning. This is a traditional one. You multiply through by a vector. P inverse, don't be put off by the inverse. It's a matrix, right? You have a matrix P inverse and you multiply both sides by it. Great. You could do right preconditioning, in which case what you're doing is you're taking, like what you're trying to do is, so left preconditioning is this. You're multiplying through on that side and this side. Right preconditioning is that you're trying to get it on the right-hand side of this matrix. So you do something like that, and it works out to that, but you generally don't solve that system. Instead, you decompose it to look like that. And that becomes easier because generally if you have P inverse, you would also have P, and now you just multiply through by a vector that you, by a matrix you already have. Oh yeah, qualities. Okay, should move that up. You could also combine them. You can multiply through both on the left and the right. And the important case for that one is if you have a symmetric matrix. So if A is symmetric and you want to preserve that symmetry, even if your preconditioner is also symmetric, the product of two symmetric matrices is not necessarily symmetric. Blah. Or you could, and I forget the name of these transformations, these matrix transformations. There's a great book called The Matrix Cookbook. It's put out by Waterloo, and it just lists all of the matrix like equations and properties and stuff like that in a super dry, condensed format. It's really good for that sort of thing. If you end up putting it on both sides of your matrix like this, then you end up preserving that symmetry. That's the benefit to the two-sided preconditioner. Okay, blah, 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 blah. Okay, recall, so now we're going to talk about the properties of this. Running low on time here. We want sparsity, and we want to keep the sparsity, right? So if A is sparse, we want to keep the preconditioner P sparse, but the inverse of a sparse matrix is typically dense. This is why we don't want to store the P inverse directly. We want to understand, we want to use its impact through multiplication, not storing it explicitly. It's a funny way to look at it. The computer algorithms, this is the way they work. Okay. Yeah, that's what this guy's all about. Okay. The best preconditioner, I guess you guys all handed in your assignment right now, right? Okay, what's the best preconditioner? A inverse, right? A inverse, you just got the identity matrix and you're done, right? The problem is that we don't have A inverse, otherwise we would be done. In which case we want to approximate A inverse, and this is the magic. We don't need the correct answer. We need a better behaved answer. If you could do A inverse, this would basically become that, right? Because you've just got 1, 0, not even, right? That's A inverse. That is the basis that you form with A inverse. Failing that, we can at least hope for something which is better behaved. And that happens when P inverse is approximately A inverse. Okay. Preconditioner qualities are based on the speed of computation and application of P inverse. If it takes longer to compute the bloody thing than it takes to solve the linear system, you haven't gained anything, right? Memory requirements for storing it, degree of fill-in, right, which is a change in your sparsity, and the parallelizability. Okay, I've got 10 minutes left, and I want to harp on this one. Yeah, okay. Particular systems. I'm running really short on this time. Okay. The easiest way to do this, and sometimes people find this for the first assignment, is called the Jacobi preconditioner. And the idea with that is that you just take your main diagonal of A and you divide through by those main diagonal elements. And that by itself is enough to improve the condition number of your system. If you do that, right? So this is an example. This is actually an example we're going to get to probably after the spring break. This is called finite different method, right? It's a real method and it results in a sparse banded matrix. I told you, these things come up all the time. Thank goodness, right? Implementing a Jacobi preconditioner, what we're basically doing is we're taking the main diagonal and we're dividing through, like a preconditioner becomes that main diagonal. Like that. And the nice property of diagonal matrices is that the inverse is just 1 over this guy, 1 over this guy, 1 over this guy, all the way down. Super easy to compute. No problem applying it. And, oh, what's going on? The hell was that? Okay, let's see the impact. First of all, unconditioned, unpreconditioned. Typo. Number, condition number, 1000. Remember, what do we want the condition number to be? Excellent, right? The preconditioned condition number is 32, which is dramatically better. Let's actually look at this, right? Without preconditioning, this starts off the residual, the relative residual starts off around here. What is that? 0, drops down to 1e minus 16 after 8 iterations, right? And the Jacobi preconditioning starts off a whole lot lower, drops off after 8, which is technically better, but honestly, meh. Okay, the better alternative is something called ILU, incomplete LU decomposition. The way it works is that we're not going to do full LU. We're going to do a little bit of LU. Typically, when you do LU, so you start off with a sparse banded matrix, LU decomposition is going to end up with a sparse L and a sparse U. I'll show you guys, right? But it'll be more. It's not the exact same sparsity. It's still sparse, but it is extended. ILU says, no. I'm just going to keep the exact same sparsity pattern. And I'm just going to ignore the rest of the terms. There's an algorithm, the way it's calculated. We're not going to cover that one. It's kind of outside of things. What you're going to end up with is, so this is our banded matrix. I think this is actually tridiagonal. Right? There are 3 of these guys. When you do LU, you end up with something like this. So you still have your main diagonal, but you kind of get these tails coming out the side. Same thing with your U. Okay? What we can do is we can do a method called the ILU-K. And what that K is the degree of fill-in. Remember, the fill-in is the expansion of sparsity. ILU0 has the exact same sparsity as your A matrix. And then you add in more and more, and it's going to add in more of these details off your diagonal. When you code it, future assignments, right? When you're coding this, you do not pass the ILU matrix. You define it as an operator, right? So this is the way you do it. You define this as SPILU. It's under SciPy sparse linalge. You enter your fill factor. I use 20 instead of 0, right? You can tell your drop rule. Drop rule is literally when you drop some of these elements so that you can keep those zeros, those sparsity. You run this thing. This is an example of how you use GMRes, right? And then you plot this guy. Without preconditioning, here's your relative residual, and it converges after about 1200. With preconditioning, it does it in 10. That is 20. That is a degree 20 fill. Right? This is ILU 20. Typically, you will not use ILU 20. You will use ILU 0. That's kind of like the default go-to. You can expand and add in more fill-in as required. But honestly, at that point, you might also just try like throwing an LU solver. Oh, those tails? Right. So ideally, you would have this completely orthogonal, right? Which would be the ideal one. Those tails are doing kind of these fine tunings. Right. It's not because it's matrices and because matrices are kind of wacky, to be entirely honest. Like it's not a trivial thing to go between those two. So I shouldn't say that those two, I shouldn't say that. I shouldn't say that the tails are responsible for this fine tuning. The entire matrix is responsible for that fine tuning. And those tails are as much a legitimate part of the matrix as any other part. I remember a colleague in Argonne who was working on these things, and we talked about it, and he said there is no reason why ILU should be beneficial. There is none. Mathematically, it is you're wishing and you're praying for convergence. That's what ILU is. There's no reason why it should converge. The fact that it does in practice is really nice, but he didn't like it because of that. Yeah. Yes.
Is there something that make it then more likely to find a nice one?
Yes. 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 Exactly. Exactly. So the ideal one is the full inverse, but the full inverse is super dense and heavy, right? So what you want is some kind of happy medium. Yeah. Had a question? No. Okay. I got 3 minutes. Okay. I'm going to skip over sparse approximate inverse. I've never actually seen anybody using it. Feel free to read that section. Right? It actually has, it looks great. Okay. Preconditioners and high performance computing. You're not going to use this. Note my hand is staying down. I'm not going to ask you to use this. When you use COMSOL, when you get out into the real world, you will definitely be using this. So this is me teaching you about this now. But it's kind of beyond the scope of practice of this course. Okay. One of the other benefits to preconditioners is when you're doing all these high performance computings, I talked about this already, right? The idea is that you want to kind of farm this out to different jobs, right? This is exactly the same as group work. You're working on a big group. You solve this, you solve this, you solve this. See you in a week, right? If you can do that, and sometimes you can do that, then that bringing together and forming like that cohesive single report is feasible. But if those things are too inseparable, then it becomes a lot more difficult to do that sort of thing, right? So what preconditioners are really useful for nowadays is accomplishing that splitting task. That's where the real practice and modern application all lie in. One of the easiest ways to do that is through something called domain decomposition. Literally what you're doing is you're taking, right? This is obviously a finite element mesh. Some of you might have actually seen it in COMSOL. I don't think this is COMSOL. I think this is ANSYS, right? These color codes are the partitioning of the mesh and therefore the geometry, right? So you guys solve blue, you guys solve green, you guys solve red, you solve orange. And we're going to have an extra overlap. And you can see there's a little bit of color blurring here. This is called the additive Schwartz method, right? And what you do is you break it up into chunks and then you have an overlap. And by iterating on that overlap, remember this is a preconditioner. You've done a decent job, but then you're leaving it to the main engine to actually nail down the correct one. That's a very common one, but completely blown out of the water by multigrid methods. When they work, but they're a lot more finicky. What these guys do is they say, okay, let's start off with a large mesh. We'll get a decent solution. And then you guys handle a closer block, and you guys handle a closer block, and you guys handle a closer block. Solve it, bring it back up, and sometimes actually go down multiple levels. Super, super efficient, nearly linear convergence on million core machines, even larger, the real flagship class in the US. Really quickly, some overtime. When we talk about multiphysics, what ends up happening is that each type of physics has its own equation. And because it's distributed in space, it has its own block in this matrix. You end up with something, I don't know why I'm drawing it when it's on the board. You end up with these blocks. If you recall, there's a special way that we can invert block matrices. If you go back and you take a look at that, there are different ways that we can precondition it. There's the equivalent to block Jacobi. You just do the inverse of that. or it gets more complicated. There are some tips down here. Parallel LU is the best. When you can and your memory is big enough, use it. CG is your next best specialized tool. Very robust. Otherwise, you're going to be doing GMRS. If you're solving a well-known problem, if you're only doing fluid dynamics, specialized software packages, specialized preconditioners, much more robust, big payoff. Otherwise, their COMSOL and like PETSI and stuff will allow you to mix and match. Super useful. If you do need additive Schwartz, what you do is use additive Schwartz to break it up. LU on each individual chunk, right? Typically, how big are those chunks? About 10,000. 10,000 to 100,000 degrees of freedom. We'll talk about what degrees of freedom are. That's your magic number, 100,000. Go with that. Geometric multigrade blows everything out of the water when it works. That's all I got. See you guys. I won't be there Monday until like 3:30 or something. But you have the timetable on there. Be prepared for the discussions and see you then.